I think we have enough people. I think I should start. All right. So welcome to another RI seminar. I guess this does not need introduction by the number of people, but I'll still do it. So Phillip is an associate professor at MIT. Before that, he did his PhD at MIT and then a postdoc at Berkeley. And Phillip has done a lot of amazing work. That's why I think there is on this cloud. The cloud speaks for itself. But just to let you know, before all this craze of DALI and all this started, Phillip was there first with Pix to Pix, and I think I would say that kind of started. I mean, there are other papers happening in the past, but that to me is the start of the craze in this whole generative generation field has been. So we should all Phillip for all this, all the climate, all everything with the 600K of spending and so on. But so yeah, Phillip has been doing a lot of this great work in generation, but he did not stop there. He has done also amazing work in contrastive learning as well. So, but today I think he's going to talk about third. So probably this is going to become the third big thing in his pillars of great things he has done. He has also done a lot of awards, as you can assume. Like after doing so many great things, you win awards. I remember a few like Pandian Research Award, Sloan Fellowship, and I'm sure there are many more there forgetting. But yeah, and so I'll let Phillip take over and give an amazing talk.
Great. Thank you, Abhinav. And I think we should also blame Junyan, your professor here, because he did all that work with me on the early generative model things, Pix-to-Pix cycle GAN. So yeah, he's equally to blame. And it's great to be back here because so many people that I know at CMU, a lot of familiar faces. It's really good to see everyone. Okay, so thank you for inviting me. I'm going to talk about this is a talk I haven't given before, so it's going to be on some new things. There won't be any computer vision, so if you are here for that, then that's not what I'll talk about. But it will be on representation learning and reinforcement learning. And in particular, I'll be talking about a goal that we've had for a long time, since the beginning of AI maybe, which is general purpose intelligence. And this is something that a lot of people are starting to talk much more about these days because, of course, we have papers like Sparks of AGI, we have GPT-4 and these models coming out that people are getting excited about, feeling like they're reaching a level of generality that we haven't seen before. And I really think it's an exciting time. Of course, this is also something that, it used to be, we weren't really supposed to use this word AGI. For years, I had to not say it. It still is controversial, but it's what I'm interested in. So I'm interested in general purpose intelligence and methods that lead toward more generality. But the current systems that are creating the buzz are systems which are, I like to think of them as models of the internet, supervised models of the internet. So they basically have, humans make the internet. That's a huge, amazing data set. And then you fit a model that just imitates behavior on the internet. Okay, so for that kind of intelligence, you do seem to get some sparks of AGI, something like that. But it's not the way that humans developed our general purpose intelligence, because we didn't have the internet. We had to make the internet. So human intelligence came about from some other mechanism. And that's what I'm most interested in. I think the last time I gave a talk here, I titled it Learning to See Without a Teacher. And I'm still trying to do learning without a teacher. How can you get intelligence in the first place before the internet exists, before human culture exists? Okay, so why would you want to do that? I don't know, but it's scientifically fascinating to me. Okay, but of course, this is an area that people have studied a lot. And one of the main approaches has been to create environments and agents that can kind of self-learn and explore the environment, do reinforcement learning, discover new skills. And I'll show you in the second half of this talk, this powder world environment that we've built, which is supposed to be more like a sandbox. This sandbox where you could learn to become skillful and recognize different types of behaviors and dynamics, not by supervised learning online, but instead by exploring and trying out everything that you can try out. So rather than imitate everything there is to imitate online, download the internet and compress it, maybe another objective that could lead toward kind of general purpose skills and abilities would be have an environment and figure out how to do everything there is to do in that environment. Okay, so that's kind of the general conjecture that we're going to be working with. We're going to try to define some structures that can make that work a little bit better. And I think in the abstract for this talk, I mentioned three things, two structures in one environment. It turned out that's too much, so I'm only going to do one structure and one environment. Talk to me if you want to hear about the third part. Okay, so structures. What types of representational structures can improve the generality of our reinforcement learning agents? That's going to be the focus of this part of the talk. Okay, so figure out how to do everything there is to do in an environment. That should lead to an agent which is capable not of just going and finding the apple, but also maybe finding the diamond. These are two different tasks, or maybe stacking the diamond on top of the apple. These are all different things you could do in the environment. And maybe if the agent just tries to do more and more things, it can come up with a more general purpose intelligence. So it's not only directed at one particular goal, but multiple goals. Okay, this is a little too grand. So in this part of the talk, I'm going to narrow it down to the task of navigating from any state in the environment to any other state. And that could also include manipulating the environment to go from state A to state B. So if I'm a robot, I could change the position of the object from state A to state B. If I'm a robot that moves, I can move my body from state A to state B. So the kind of interesting and unfortunate thing about a lot of reinforcement learning, I think, over the last decades is it's been targeted at fairly narrow abilities. Let me get a high score in this one video game, or let me get this one robot to perform one manipulation task. And instead, to reach more generality, we want to have reinforcement learning agents that can be conditioned on a goal or follow an instruction to achieve more than one thing. Okay, so this is a very simple example of more than one thing. Get to apple and get to diamond. So how would you solve this with reinforcement learning? Okay, so one way you could do it is you could learn a value function. This is one of the kind of fundamental objects of reinforcement learning. And since I like to think of things as representation learning, you can kind of think of this value function as a good representation of the environment that would enable a planner to act optimally. So the value function is going to, if my task here is to get to the apple, the value function is just going to be the distance from the apple. So it's going to be the cost of the optimal plan to go from any state to the apple. That's my value function v. In this talk, I'm always going to be talking about optimal value functions, or almost always. So that the star means optimal value function. That means if I'm an optimal agent, what's the cost of getting to that apple? That's what the value function reports. And it's with respect to the goal of getting to the apple. Okay. If I change my goal, I will say, now the goal is to get to this location. Now my value function is the value of every state with respect to this goal. It's a different goal, so the value function changed. And a planner or a policy could just follow the gradient of the value function, and that would give you the optimal sequence of actions to get to the goal in the fewest number of steps. Okay, so this is classic value learning approach to reinforcement learning. But usually people have a different value function for every different goal that they define. And what I want to argue is that actually there's a lot of structure that's shared between the value function for every possible goal you could define in this environment. And then we'll develop an algorithm, a kind of general purpose reinforcement algorithm based on that idea. Okay, so the question is, how do you model the optimal value function v star for all goals, not just get the apple or get the diamond, but one for all goals? And that's a function which is a little bit different than your typical reinforcement learning value function. Sometimes it's called the universal value function because it's a function of not just the value of the state with respect to maximizing one reward, but it's the state with respect to maximizing a variable, any variable goal. So it's a mapping from state and goal to the value of the state with respect to that goal. This is called the universal value function. It's a little bit less studied, but I think it's actually the more important object and the one that we're most interested in for agents that can exhibit goal-directed behavior toward multiple goals, solve more than one task. Okay, so how do you model that? So the first answer will, of course, be just use a neural net. Like, why not? Like, that does everything. So you could just say, I'll have a neural net. It could be a multi-layer perceptron. It could be a transformer. It could be any kind of neural net. It's a universal approximator, so it should be able to learn with enough data to approximate whatever the target function is. And people do that, in fact. So some of the early work on universal value functions just used a neural net to fit your universal value function in the same way that you'd use a neural net to fit your traditional state value function. Okay. But we can actually do a little better because it turns out there is structure in the universal value function that can be exploited. It's not just an arbitrary function that you would want an arbitrary function approximator to fit. It actually has a lot of structure. And the main structure that we'll be exploiting in this talk is going to be the triangle inequality. Okay, so the triangle inequality always applies for any optimal value function for any MDP, for any Markov decision process. So basically, for any RL problem, the universal value function is a function that satisfies the triangle inequality if it's optimal. Okay, so intuitively, the way to see that is that if I want to go from state A to state C, that distance cannot be longer than going from state A to state B and then going from state B to state C. Okay, so going from state A to state B, the optimal plan from state A to state B plus the optimal plan from state B to state C is always at least as long and maybe longer than the optimal plan from state A to state C. Intuitively, the reason is because this would be one possible plan. And if it's the best plan, then we have equality, or it could be a better plan. Or there could be a better plan that goes directly from state A to state C. So in this Euclidean space, in this actual like maze that the robot is going through, that makes a lot of sense. The shortest path is a straight line, and you can never, the Euclidean space follows the triangle inequality. Okay, so optimal value functions follow the triangle inequality. That's a huge amount of structure. That tells us that if we know something about the value for state A and state B, this value function, and we know this one, it constrains something about this one. It gives us this inequality constraint. Okay, so that tells us that there's shared information, shared structure between all of my different value functions for all the different goals I could specify. If I learn the value function for one goal, it tells me something about the value function for other goals. This is the relationship that shares information. Okay. My battery might be running low. Let's see. Okay, there we go. So how can we exploit that shared structure? And the first idea might be to do metric learning. So what metric learning does is it's basically learning a metric function, and a metric is defined by it being a function that satisfies the triangle inequality. Metrics also have a few other properties, but the main one is that they satisfy the triangle inequality. Okay, so how do you do metric learning to learn a value function between two states? It's the distance function between state and goal. Well, the typical way might be that you will learn a representation of your state and a representation of your goal, and then apply a distance metric like the Euclidean norm to the two learned representations. And this Euclidean norm, it's a metric function that satisfies the triangle inequality. So any setting of the parameters down here, any representation will result in a metric that satisfies triangle inequality. And you can learn the parameters to find the one that actually fits your value function. That would be the metric learning approach to learning a universal value function. And I'm going to be talking about a slightly different version of this, but it's going to share the same structure. And it's going to reflect the property that universal value functions are not symmetric, typically. Okay, and metrics, the other property, they're triangle inequality, they satisfy that. And the other property they satisfy is that they are symmetric functions. So for a metric, the distance between a state and a goal is the same as the distance between the goal and the state. V star s comma g would equal V star g comma s for a metric. And it turns out that for most reinforcement learning problems, they're not symmetric in that sense. So here's an example. So let's go back to our maze with the robot in a room. And if the doors are all open, then the distance from any state to any other state, the shortest path between any two states, will be symmetrical. But what if the doors are one-way doors? What if you can only go through them in one direction? So if that's the case, then the distance to go from state A to state B might not be the same as the distance to go from state B to state A. So here, the distance to go from this room to that room is really long. You have to go out that door and in this door. You can't go through that door. It's a one-way door. But the distance of going the opposite direction from here to here is really short because I can just walk through the door. So whenever you have one-way doors, you get asymmetrical shortest path between states. Shortest path between states is the optimal value function for a state and a goal in this navigation problem. Okay, so that can be asymmetric. We can't use metric learning. And this is all over the place. So whenever I have one-way doors or one-way streets, if I'm doing self-driving, I want to navigate a city, a lot of the streets are one way. That means the cost of going in one direction is not the same as in the other direction. Walking uphill is asymmetric. The cost of going from the bottom to the top is a lot higher, a lot more energy than the cost of going from the top to the bottom. Okay, this is just some funny thing. Maybe this is from CMU. I don't remember, but probably this is probably MIT. Actually, I'll say this is probably the MIT robot. I can't remember. Anyway, it's really easy to go from standing up to falling down, right? That plan is really, really simple. Just fall over. But going from falling over to standing up is much, much harder. Okay, an escalator is a one-way street, and time, just time's arrow. Almost all physics dynamics problems, continuous control problems, are going to have this asymmetry where going in the forward direction through time, the control problem is different than if I were to turn time backwards, right? There's an arrow to time. Entropy increases, gravity brings things down. You have to work to go against gravity. So essentially in physics, there's a lot of asymmetry, at least at the macro scale. Okay, so what is the object that's like a metric that satisfies the triangle inequality, but is not symmetrical? And you might not know this word, but I think it's an important word. It's a quasimetric. Okay, a quasimetric is a possibly asymmetric distance function metric. So it's a metric. It has the triangle inequality. It's non-negative, and it has this thing called identity of indiscernibles. That just means that the distance from a state to itself is 0. And those are the only 3 properties that are satisfied by a quasimetric. So it's missing the additional property that a metric has, which is symmetry. Okay, so quasimetrics are actually, I think, a really important class of functions, maybe as important as metrics, right? There's a whole field called metric learning, and I'm suggesting we should have a field called quasimetric learning, and we've been starting to work on that. Okay, so metrics are a subset of quasimetrics. They're the subset that is symmetrical functions. They include things like Euclidean norm, Manhattan distance, all these types of things. Okay, quasimetrics include a broader set of things. They include conditional entropy. They include the shortest path on a directed graph. And you can also have unconstrained functions that are outside that set. Okay, and in particular, one thing that we've proven is that the value function, the optimal value function, is always a quasimetric. I showed you the intuition that it would satisfy the triangle inequality. And additionally, for any quasimetric function, there exists an MDP, a Markov decision process, for which the optimal value function is that quasimetric. So what this says is that the space of quasimetrics and the space of optimal value functions are identical. They're the same space. Okay, so that just tells us that in quasimetrics we have the optimal value function, or the cost of a optimal plan to go from a state to a goal. And that's a very fundamental, important object for all these types of reinforcement learning and planning problems. Okay, so how should we model V star for all goals? Well, metrics won't work because they're symmetrical, so let's just use a quasimetric. And it's going to be, I'm going to show you a construction very briefly, but it's going to be a function over latent variables, representation Z1 and Z2, which is a quasimetric function. And the parameters to learn the right quasimetric that fits the data are going to be in the embeddings of the state representation. So I'll represent the state and the goal, and then I'll measure a quasimetric function between them. Just like for metric learning, we learn embeddings, and then we apply a distance metric between the embeddings. Okay. Okay, let's look at this one more time. And here I want to emphasize the distinction between single task reinforcement learning and goal reaching reinforcement learning. So in single task reinforcement learning, the non-generalist agent, the agent that can just do one thing, we have a value function, which is a mapping from the state to the predicted value, which is the expected reward that you'll get if you act optimally from that state on forward. So it's the cost to go, how much distance do I have left to go on the optimal path to the goal. Okay, so this is the V star S that we're all familiar with in reinforcement learning. But in goal reaching reinforcement learning, the universal value function is a mapping from state by goal to the value. And in single task RL, this function, well, the value function for MDPs could be anything in all functions from state space to scalar value. But in goal reaching RL, this extra structure emerges that unites all of the goals. So the set of value functions for all MDPs is a subset. It's a much smaller space than the full unconstrained space of all possible bivariate functions of state to value. Okay. So basically, the idea is going to be if we learn value functions that are constrained to be Quasimetrics, it'll save us a lot of computation because we will be sure we're not outside of the set where they could possibly be found. We know that the optimal value function for goal reaching RL has to be in that yellow region. So why don't we constrain ourselves to only look in that yellow region? Okay, so that was a whole lot. So I want to pause for a minute and give a recap of what we've seen so far. Okay, so one is that generalist agents should be able to reach any reasonable goal from any reasonable state. That's kind of one idea of what we would want with maybe a household robot that can rearrange anything into any new configuration in our house. Okay, so what is a data structure that helps that? It would be the optimal value function for telling me the cost to go from state to goal for any state and any goal. Okay. Now, what I've told you is that that function is always a quasimetric. So we should model it as a quasimetric, because if we model it as a quasimetric, we'll essentially be enforcing constraints that unite different goals. So there's this triangle inequality that tells me that if I know something about state A and goal B, and I know something about state B and goal C, it tells me something about state A and goal C. So there's shared structure between all of these state-goal pairs. Okay, learning to solve one task, learning to reach one goal informs how I can reach another goal. And that should lead to faster learning, better generalization. It should just be a good thing to do. Well, theoretically, so I'll get to the practical results soon. We'll see if it's actually a good thing to do. Okay, so I'm really excited about this area of quasimetric learning. And to make progress on this, we had to first come up with tools for learning quasimetrics, which are a little bit different than metrics. I'm not going to go into the full details of this. I'll kind of tell you the gist of it, what we got to, and then I'll show how to use it for reinforcement learning. But if you do want to read up on just like the machine learning of how do you model a quasimetric function, there's only about 4 papers. There might be 1 or 2 more that have come out since I made that slide. But in this era where there's 1,000 new diffusion models every day, check out this, because you only have to read 4 papers and you'll be right up to date. Okay, so I like this because no one else is working on it, or except for a few people, but good people, Jimmy Baugh, right, Peter Stone. Okay, and then these are the bolder are 2 papers. Okay, so I'm not going to work through all the derivations behind this, but the way that we model quasimetric functions that I'll be using for the reinforcement learning algorithm that I introduce is going to be something called an interval quasimetric embedding. This is my student Tongzhou, who's been the lead behind all of this, came up with this method, and it is a function d latent, which I'll tell you about in a second, which is a quasimetric function, and then you learn parameterized state representations. And so the machine learning goes on to fit the parameters down here to find the quasimetric that fits the data. And this has the property that all functions in this family are quasimetrics, and it has universal approximations. All quasimetrics can be fit in this fashion. Okay, so I don't expect you to understand the intuition behind this. I just wanted to show you the equation. It's about 10 lines of PyTorch that can implement a quasimetric between 2 vectors u and v. So if I have these 2, a state embedding and a goal embedding, and I want to compute the quasimetric distance between them, then you use this particular equation. But let me just point out the kind of qualitative thing that's important here. The important thing is with a metric function, I would take the difference, this minus that plus that minus that, or this minus this squared plus this minus this squared of its Euclidean distance, right? And sum them all up. And for quasimetric distance, it needs to be asymmetrical. So there's got to be something like a ReLU in there or something that's asymmetrical. It has to be the case that if I flip the order, if I swap u and v, I'll get a different answer. And the asymmetrical part in these interval quasimetric embeddings is this thing, this max between the value in the u vector and the value in the v vector. And then we're looking at the interval, the length, going from the value in the u vector to the max of the value in u and v. And so because this is not v, that's a special rule for u. And basically, I'm measuring this distance between the blue point, how far to the right is the red point from the blue point. But if the red point is to the left of the blue point, we get 0 interval. That's the asymmetry. And that can be implemented in a few lines of PyTorch. And why exactly this is a universal approximator, read the paper. There's a lot of Tongzhou's math behind it. Yeah.
Right?
Yeah.
What are the two indices, I and j?
Just indices of the vectors. Oh, there's a group. You have actually a group of u sub 1, sub 2, sub 3, sub 4. So you have a group of vectors. It's a matrix. Like,
Group mean what? Like multiple states? Or I thought U and like V is the goal state, U is a starting state.
that's right. So instead of being a vector representation of the state, it's a matrix representation. So you embed into a set of vectors, essentially. The state representation is a set of vectors, U1 through UK. If that makes sense.
Vectors instead of just one single long vector.
Not sure. I don't actually have a good intuition for this myself, but essentially you kind of get it by first you have this idea of you're having quasi partitions, which are just a partitioning of the space, and then you take an expectation of them, and that's where the sum comes from. But we can talk offline about the details. I think it's a kind of opaque equation just to see. I just wanted to show you what it is. Yeah.
The max is a design decision, or there's something special about max that we have to read paper to
The max, so you need some kind of asymmetrical function, and the max is gonna get you that in this example. It's a design decision. There's a few other ways of doing it. We have another one in the previous paper called Poisson Quasimetric embeddings, which doesn't use a max, so that's kind of a design decision.
pretty much anything.
Not anything. You still have to be able to prove universal approximation. So I'll say that Tongzhou's very careful with the math to make sure this satisfies universal approximation. That's why it's tricky. That's why you can't just take a ReLU or some random function. Okay. So yeah, we have 2 whole papers on that. So do check them out. But I didn't prepare a whole set of slides on them because I want to get to the RL algorithm. And Tongzhou has this great Torch QMet package. If you want to use Quasimetrics, then this will implement all the latest, greatest Quasimetrics. There's only 4 of them, so this will implement all 4. Okay, so now we have the machinery for modeling quasimetric functions. I told you that the optimal goal-reaching value function is a quasimetric. Now we're going to put all those pieces together to come up with a new RL approach that solves reinforcement learning, goal conditional reinforcement learning with quasimetric learning. Okay, and I'll show you these animations in a second, but I made a physical version of this. It's a little hacked together, but maybe you can see. Okay, so let's say I have a graph here, right? I have 3 nodes on the graph. These are like laundry balls to keep the clothes dry. Okay, I have three nodes on this graph, and I want to find the shortest path between node in my right hand and node in my left hand. So how do I do that? I can just do this. I just pull them apart. And notice that the path that appeared at the top path, that's the shortest path. Okay, if I take this one and I just the distance from here to here is exactly proportional to the optimal value, V star, between here and here. It's exactly proportional to the shortest path distance from here to here because gravity is pulling down. Okay, same for here and here. So what is the intuition? The intuition is that as I pull apart connected nodes in a graph, the shortest path is the most constraining. I can't pull my hands apart farther because the shortest path is the thing that first stops me from pulling my hands apart. Okay, and this is not an approximation. This is, I mean, it's an approximation in the sense that there's friction and stuff like that. But this is actually a way of finding the shortest paths in a graph. Just pull apart the nodes until you reach the limits of how far apart you can pull. And that's how this algorithm is going to work. Okay, so here's an animation of that process. Oh, here we go. So we're pulling apart the start and the goal on a undirected graph. And what is revealed in red at the end is the shortest path from start to goal. Okay, over here, we're pulling apart these 2. This is start, this is goal. As we pull them apart, the maximal distance between them, if these are hard constraints, these are edges that can't stretch, is going to be the shortest path. It kind of makes sense. Just imagine you have these ropes or chains. You're pulling things apart. The shortest chain, the shortest path is the thing that first stops your hands from moving apart. That's the whole intuition of the method. Okay. So let's now prove that and show that that's really that really works. Okay. So we have a problem, a goal-reaching reinforcement learning problem, which can be represented as a directed acyclical graph, a DAG. And so the environment dynamics are, I can go from this state to that state. there's some cost. I can go from this state to that state. I can go back. I can go here. I can't go back on this one. So it's a directed graph. It's asymmetrical. That's why we had to use Quasimetrics, because most environment dynamics are asymmetrical in the problems that come up in life. Okay, so our task is to learn a parameterized function d theta. That's going to be our quasimetric function. And we want it to equal the optimal value function, v star, between all of these nodes. Okay, so we're going to do this in 2 steps. The first step will be we'll just learn the adjacency structure, the local cost structure of which nodes are connected to which nodes and what is the cost of moving from each node to each connected node. We'll just learn the local structure, and then we'll globalize to be able to find the minimal cost to go from any node to any faraway node by this pulling apart operation. And then we'll prove that that actually results in the true optimal value function. Okay, so first step is going to be supervised learning. It's going to be, I have some way of sampling states from the environment. Okay, that could be, I have an offline data set in RL. It could be that I kind of explore for a while. I have trajectories, and I observe all of my state, next state transitions. Okay, so sometimes I was in the yellow state, and then I got next to the green state. So these are all the local transitions. If I have a data set, I can then train my cost, my distance d theta function, such that all of the local transitions have a cost. We simplified it. We said the cost is just 1. We're going to say every edge is length 1. That can be relaxed. The actual transition cost can just be the reward function. That's the definition of a reward function. The cost of going from state A to from state S to state S prime, given an action A. So that's the reward function. But we simplified it for analysis here to just be cost 1. Every edge is cost 1. Okay. Okay, so if I train my cost, my quasimetric d theta, such that all of my transitions have cost 1, so d theta accurately represents all local costs, and I did that for every possible transition if I had enough data to do that. Then I'm going to just do this globalization operation, which will be pulling apart all the nodes. And we're not going to pull it apart in our 2D physical space. We're going to pull it apart in high dimensional space. Okay, but it's the same kind of idea. So now what we're going to do is we're going to say one is d theta is a quasimetric because we're using our interval quasimetric embeddings as our parameterization of d theta. And those interval quasimetric embeddings can only represent quasimetric functions. So this is a hard constraint. This is guaranteed by our parameterization of d theta. Okay, that's the previous work. Just take it as a given that we can do that with these interval quasimetric embeddings. Okay, so if it's a quasimetric, we know that d theta follows the triangle inequality. So what does the triangle inequality say? It says that the cost, the optimal path length from red to green, from any one node to any other node, is less than or equal to the sum of all the cost on all the intervening links. So for any path through this graph, the sum of the cost of all edges along that path is going to be at greater than or equal to the shortest path between the two nodes. So this is just an extension of the triangle inequality. Okay? So under these constraints, under the fact that we represented all the local costs, and we know that the sum has to be, the optimal distance has to be less than the total cost along any path. That means it also has to be less than or equal to the total cost along the shortest path, because the shortest path is one of the any paths. So this is also following from the triangle inequality. Okay? Now I do the final thing, the pulling apart. Now we just we train our theta, we maximize over parameters theta to find the quasimetric that places the highest distance between these two states subject to these constraints. And that's going to be exactly equal to the minimal path length, okay? Because as I showed, we have an inequality here. So if I maximize this side, then the max it can possibly be is going to be equal to the shortest path length. Does that make sense? Okay, we maximize that inequality, we got equality, and the minimum path length between these two, the minimum cost of any path between these two nodes is the definition of the optimal value function, or the negative of the optimal value function. Negative just convention, because values are telling you how good, like the cost is the negative of the reward idea. Yeah, so just a convention that value functions report, how good the state is, not how bad the state is. Yeah.
Discounting.
No discounting here. Yeah. Okay, so you can relax some of those assumptions. These don't have to be unitary cost, but this is just the simplest version. Yeah, question.
So are you assuming that the MDP has to be a DAG for this to work, or
Yes.
like isn't that a very constraining assumption? Like basically a lot of the MDPs I can think of, you can form cycles, right?
Yeah, so that is simplifying. I mean, that applies to a large class of problems. So all of these like navigation problems, object rearrangement, tabletop problems. So it's a large class of problems for which you can represent them as a DAG, and it might not be all possible problems. Yeah.
Problems with DAG, you can like get back to the same state, right? So would that be that would not be acyclic, right?
Oh, the acyclic property of the DAG. Oh, yeah, actually, I probably should not have called it a DAG. It's not, it can have cycles. Yeah, no, the graph can have cycles. Yeah, I think I just had a typo there. Yeah, and then I said it, sorry. You can have cycles. Okay, like, let's see, here's a cycle, right? Okay, so it's just a directed graph. Yeah, get rid of the A. Yeah, sorry about that. Okay, so what we did is we found the optimal value between these two nodes, but how to find it between any other nodes, just repeat the whole process again. And just for all possible state pairs, state one goal, state two, another goal, find the parameters that maximize that function. Okay, so it's like pulling apart all nodes in hyperdimensional space. And that will recover my true optimal value function if I have high enough dimensional space and enough parameters, under sufficient conditions. Question in the back.
So if it's a directed graph, then
Yeah.
how does the pulling work? If you pull it, it may not have that direction. That direction may not work, right?
You can still pull, and it's still a directed edge. It's just you're pulling directed edge. So that's the physical analogy here is a metric space, because the physical Euclidean space is a metric space. So this analogy doesn't quite work for DAGs, but directed graphs, sorry, they still satisfy the triangle inequality. And that's really all you need for this proof to follow. Yeah, Deepak.
So I have two questions. One is, how are you learning this d theta? Like, is it trained on a data set?
Yeah, I'll throw that in the next slide.
Okay. Second question is, this property, this equation at the very end, this
Yeah.
still holds true for symmetric distance, like L2
It does.
distance, right?
Yeah.
So this is a property which holds true for any distance, be it
Yeah.
quasi-symmetric or symmetric.
So quasimetrics include metrics. So this is also true for symmetric problems. Yeah, that's a great question. Shubham?
Basically, this slide I could have also applied if I were learning a regular metric for
That's true. So this works for regular metric learning too. But maybe that's more old, and the quasimetrics are the newer part and the more exciting part, because most planning problems are quasimetric. Okay, so Deepak asked a great question. How do you actually train this? So what you do is you have to have a way of sampling random states, random goals, and transitions, S, A, S prime, state, action, next state. And if you do offline RL, that's kind of the setup. You just have this in some buffer in offline RL. That's your training data. If you do online RL, then you have to couple this with some exploration algorithm. So it's not really any different than other RL methods where you have to, do some trajectories. You collect data from those trajectories, sample random states and random goals from your buffer. It could be a replay buffer. Okay, then this is the entire optimization algorithm. So you maximize the distance between the quasimetric distance between all states and all goals sampled randomly from your distribution over states and goals. And you subject that to the constraint that that all of the local costs are unitary, or this could be replaced with the reward function. And if you violate this constraint that you actually fit the local transitions, then you pay some penalty epsilon. Or you can say that you're allowed to violate it by amount epsilon. Okay, and we're only searching over d theta, which is guaranteed to be a quasimetric because we're using a parameterized family of quasimetrics. Okay, so pull apart and capture the local constraints. Make sure that you don't violate the length of these individual strings, these edges. Okay, so then theoretically, you can prove that given enough data, given enough model parameters, that this can recover the true value function. Okay, the optimal value function. Okay, so one more way of looking at it from this kind of function space diagram. So we start with the space of all functions, and then we say, no, we'll only consider quasimetrics because we know that our optimal value function is a quasimetric. Okay, so now we have a parameterized family of quasimetrics. That was the quasimetric learning slides. Okay, then what we do is we say, we know that the distance between a state and adjacent states has to equal the reward or equal unitary cost, if we make that assumption. And that's a subset of all possible quasimetrics. That's quasimetrics that capture local distance. And then if we simply maximize all the other possible state goal pairs, then the final remaining point is the optimal value function. Okay. So let's get to some experiments. And then I'll also have a short section at the end of this talk, which is no math and just fun powder world environments. Yeah, bear with me so that we have a little bit of fun stuff at the very end. Okay. So we're going to do some experiments on mountain car. So mountain car is you take this car and you want to get to some goal. The typical goal in single task RL is just to get to the top of the mountain. But in goal conditional RL, the goal is to get anywhere at any velocity. So you can specify any velocity and position, and that can be your goal. Okay, so this is what the optimal value function looks like in mountain car. So mountain car has two states. It has the velocity of the car, and it has the position of the car, the x position of the car. And if my goal is to get to the top of the hill, then this is what the optimal value function looks like. The top of the hill is over here, and so this is actually not the value, but this is the distance, so the negative value. And at the top of the hill, you get 0 distance. Okay, so the planning would just mean walking in the direction that descends the gradient of this image, essentially. Walk to the next state that has the shortest path to the goal. Okay, so here is the optimal value function for the top of the hill. Here's the optimal value function for a different state. Here's the optimal value function for a different state. Quasimetric structure, the triangle inequality, relates all of these optimal value functions. Our method uses that, other methods don't. So here is the optimal value function inferred by quasimetric reinforcement learning. And there's some errors down here where there was really no feasible path, but otherwise it basically gets the structure decently right. Okay, once you have the optimal value function, you can then do planning or train a policy to use that function to achieve high rewards. So we're really just focusing on the value function here. Okay, what about if I get rid of the quasimetric and I just use a metric embedding? Okay, we said that most problems are asymmetrical, and mountain car is very asymmetrical. Okay, going downhill is different than going uphill. The dynamics are different. And if I use a metric embedding, then I don't really capture the true optimal value function, because the true optimal value function has quasimetric structure. Okay. What if I use Q-learning? Q-learning can recover the value function, but it is using this kind of bootstrapping process that can be fairly unstable. And in these cases, it kind of failed to converge. Okay. What if I replace the Q function in Q-learning with a quasimetric function? So it's not really redoing the whole algorithm. It's still doing Q-learning, but just the Q function is constrained to be a quasimetric. I'm using my interval quasimetric embeddings to learn Q. That actually works decently well, but I'll show you that it fails in a different setting. Another related method is called contrastive RL. In contrastive RL, it's very similar. You're pulling together adjacent states, and you're pulling apart random states and goals. Recent method, and it doesn't work too well in this setting because contrastive RL doesn't learn the optimal value function. It learns the on-policy value function. So this is, for a bad policy, the on-policy value function is not very close to optimal. And contrastive RL with a quasimetric distance function also doesn't work that well. Okay, Deepak.
Just one slide, I can show QRL again. Like you are not doing any there's a QRL slide. Yeah, you're not doing any bootstrapping in this. You're directly regressing every state. No bootstrapping. No bootstrapping, right?
Yeah. So this is the entire optimization. So there's no temporal differences. There's no bootstrapping, which we think is a desirable property. Okay, yeah. What's that?
How do you optimize it by ensuring like these constraints?
This is just gradient descent. So you use SGD or Atom or something.
The constraints.
The constraint is using a kind of Lagrange multiplier method. Yeah. Yeah, question.
Perhaps a kind of basic question. So let's say I take goal and I just append it to my state, but I've transformed it in fact into a single problem. And then I use something like the element resistance optimization, right? And we know that because the shortest path is gonna use all the other shortest paths, right? Because it feels like we should just learn Quasimetric. So in the plot you just showed, it seemed like you did something like that, it didn't work. And I'm curious, like, it seems like conceptually that should work. So do you have a sense of why it didn't work?
Okay, I think I need to think through the question a bit more. Maybe we can take that one offline. It'll take a little more discussion to go through that. But I don't think this is the unique way to solve the problem. Maybe there's some interesting construction with concatenating states and goals. Yeah, let's talk offline about that. Okay. Yeah.
Q-learning part, is that also happening on offline data or is it happening on online data?
That was Q-learning on offline data.
So my hypothesis is that if you are doing bootstrapping using an L2 loss, like some symmetric loss, it should still learn a quasimetric at the end of the day.
It should. If you have enough data, it will recover the true value function, and the true value function is a quasimetric. The only reason to do this is the same reason we use CNNs and transformers instead of
it is not learning here, right?
It is learning.
The Q-learning part should also learn quasimetric.
It just failed. Yeah, with enough data and perfect optimization, then all methods will converge on the truth.
Bootstrap will constrain it because there is no way it can be symmetric and satisfy bootstrap.
Yeah, the Bellman update is a quasimetric. So I mean, it is enforcing that kind of quasimetric inequality. That's like the Bellman inequality. So yeah, I'm not quite sure why this failed, but I think it's just instability of Q learning.
Enough data in this region.
Yeah, PD methods might kind of accumulate errors. I think that's what's going on here. Okay. So I think I'm going to skip the online experiments, but suffice it to say that you can also do this for online RL. You get state-of-the-art performance. You can compare to DTPG with hindsight experience relabeling and things like this. And it does a little better. Okay. So what makes QRL different from other RL methods? The main thing is optimality without policy iteration. So you're recovering the optimal value function directly. And the other main thing is that it's making use of this quasimetric structure, which is just something other methods don't directly do, except via maybe these Bellman updates indirectly. It's also free from bootstrapping and temporal difference. And one limitation is that it doesn't handle stochastic dynamics. It might not apply to all MDPs. You need to be able to represent them as directed graphs. And so empirically, it still actually works well on problems that have stochastic dynamics, but it's not universal. It can only handle a certain class of problems. Okay, so I did want to show this, and we don't have too much time, so I'll go quickly through a completely non-math, just fun environment. But the bigger picture here is that I think we don't only need new data structures and algorithms for multitask kind of goal-reaching behavior, instruction following behavior. We also need environments that support being able to do all kinds of things, not just one thing, not just one score in the game. And we kind of made this sandbox environment that we call Powder World. This will be presented at iClear, and this is work that Kevin Franz has led. Okay, so it's kind of like a big ImageNet style set of environments, but rather than being all hard-coded, they're procedural. I think these ones are all made by Kevin, but we have procedures now. Okay, so you can try this out. Here's the demo you can try online. And this is based on this genre of games called powder games. They were popular in the 90s, I think. And basically, you can add plants, and the plants will grow into water, and then you can ignite the plants with lava, and they'll explode. And there's all these different elements, and they all kind of interact combinatorically. And we even have like voids, birds that will flock around, and fish, and other things like that. Okay, so this is all implemented as cellular automata. So there's a cell state, which can be a high dimensional vector, so that could actually capture a lot of complex information if you wanted it to. The elements all interact according to some set of rules that we've coded, or Kevin has coded. And all of the rules are implemented as convolutional kernels, because a cellular automata on a grid can be represented via these convolutional kernels. And that means that it all runs on the GPU and is written in PyTorch using CUDA kernels. So here are some of the rules, like if there's ice, and it touches water, the water might freeze, the ice can melt. And this kind of creates a little physics world that runs on the GPU and is really fast. A few more demos. Okay, water flows, sand piles, wood burns, plants spread out, the ice melts, gas rises, dust explodes when it hits lava or fire. Okay. And this environment, one of the main selling points is because it runs on the GPU, it's very fast. So here's Atari. This is number of time steps per second. So higher is better. Atari is 10 times slower than 32 by 32 powder world. Things like Crafter or Minecraft are quite a lot slower too. Okay. So we are interested in proposing this as just a kind of playground for a space where agents could make up their own tasks, could explore a wide range of tasks. And here are just a few of the examples. Here are some lemmings that we need to cross this lava, so they'll follow each other, and the agent, the user, the policy will have to make a ramp or a bridge to get them to the green area. There's a lot of different tasks that can be encoded into this space, and there's a little simple API for it. Okay, we really want to explore and propose a big space of tasks. So you might have different types of reward functions, like get the water into a location, or get the lemmings into a location. There's different states. There's all these different elements, and we could add more. And then there's different actions. What can the user do to control the behavior in this world? What kind of elements can you place? There's wind. Where can you place wind? What kind of force of the wind can you apply? And we want to kind of propose this as this multidimensional space, multitask space, where different corners might be one set of tasks. These are all like burning the plants tasks in a sand world. And over here in a different corner, we can test generalization to a very different type of task. This would be a building a bridge task between two regions. Okay, so yeah, I think I'll just advertise this as an environment to go check out. We're still now using this environment to study generalization, what happens when you try to train agents to do more than one task, this continuum of tasks, and I just think it's a fun environment. So putting that in there. So let me summarize. So I think multitask is the future, it's the present. We're getting closer to what we might really want to call general intelligence, and large language models are one way, and I do think that's super compelling, but it's also interesting to consider how you do it without the internet. How did biology do it? Okay, multitask is different. Single task has different structure than multitask. Certain structures appear only when you move to this goal conditional setting, and one is quasimetric structure. Okay, but we also need environments and benchmarks for studying agents that can solve many different tasks. So instruction following, for example, you just type in a task and they solve it. And that's an area that I think a lot of interesting work is going on at CMU for robots that can follow some instructions. Okay, and then I think rather than just imitate everything there is to imitate on the internet, another approach to getting closer to general intelligence is train agents that can be put in an environment, kind of figure out how to do everything interesting in that environment. We might need to define interesting, but that's another open problem. Okay, so this work was, all the Quasimetric stuff was done by Tongzhou in collaboration with Antonio and Amy, and then Kevin did the powder world. So thank you and happy to take questions. Oh yeah, let's do that first. Yeah.
Can I ask a question?
Yeah.
So in robotics application, we are learning the value function for all the goals, and it's a very high dimensional problem, right? And how do we think of applying in robotics tasks? Because those are very high dimensional tasks, and on like online learning and stuff like that, like when we don't know the goal ahead of time, and in the environment we try to learn the goal and do something, then how can we apply that?
Yeah. So what if you don't know the goals? How did we just like come up with this goal set? So in the problems that I was showing you, what we're actually doing is just saying that any state can be a goal. So the goal is get to state X for any X in the state space. And then it's just essentially planning to go from any state in state space to any other state in state space. In the paper on the QRL, you can see that actually you can define goal sets, which are not just a single state, but the goal set is a set of states. And if you get to any state in the set of states, then you've achieved the goal. I didn't really talk about that, but that's a small modification. But this still requires you to specify your set of goals or your goal space. How do you come up with goals in the first place? How do you infer goals from data? That's another open question, and this work doesn't really address that.
Slightly related to that, so the assumption is that you said, right, that goals are states, but often when we specify goals, we have some other descriptions of them. And so it may not be a goal as a state, but goal as a descriptor or an image or something.
Yeah.
And do you think there is still some structure that applies in that setting where the goal space isn't really a state or a set of state space, but some other description?
I think so. Well, I do think that goals as sets of states might be very general. Maybe you can turn any problem into that, but it might not be the most natural construction or efficient one. I think like reward functions, some continuous reward for every single action you take it's not always trivial to turn that into one of these shortest path problems to achieve a goal. So yeah, I think that finding out how to use quasimetric structure and use this kind of algorithm there is important and an open question. We don't have a system that naively could handle like an arbitrarily specified goal as like a function of all the activity that you're doing. Yeah, but that would be really interesting. Okay, let's go over here.
So have you compared the long horizon capability of QRL with other baselines? Yes.
Long horizon capability.
Q-learning based approaches.
I don't think we've specifically looked at long horizon, except insofar as some of the tasks have a medium horizon. None of the tasks are like super long horizon tasks. They're like fetch and pick and place and move to location. So I think the horizons aren't probably in the category you would want as long horizon. So we haven't looked at it. Yeah. Okay, maybe we'll go to the back. I saw the hand.
Yeah, so for the longstanding test environment that you have is a benchmark for multitask learning. And a lot of the tasks that you said were first predefined and now are procedurally generated. And when you are trying to solve these multitasks, you have to have some sort of definition of what is the task, which requires this domain knowledge that you're really inserting into it. So what I was wondering is, how do you balance that domain knowledge that's external and the maybe some of this quasimetric or items in the environment that you're talking about?
Yeah, so in the environment stuff, there wasn't really a tight connection to quasimetrics. So that's, I mean, that would be cool to find some quasimetric task space over that complex an environment. But yeah, we want to have kind of the space of all interesting tasks, but you have to have some human right now define what are this set of interesting tasks. I mean, I've always wanted to do something like game of life, where you just like have an agent that learns to do anything that can be done in game of life, but it's too hard. It's Turing complete. It's just, that's everything. So here, what we do is Kevin designs a bunch of tasks, and now what he's doing is writing them in a kind of scripting language. And then the next step, which I'm excited about, is have a language model that will automatically generate tasks in that scripting language. But he defines the API for that scripting language, which tells you that these are of human interest to one human. Yeah, so I think you do need to add that structure. There's not like an obvious way for me that I can think of to make it completely like algorithmic. Let's go to the front.
So I don't know if this is something that I just misunderstood, but there seems to be some maximization that happens between like any set of states.
Yeah.
And in the case where you have some sort of grid world or discrete states, this is feasible, although like it does like kind of like explode once you have like a lot of high dimensional states.
Yeah.
But I'm curious if there's any way to do this in the case where you have, say, like images as the goals or images as a state.
So yeah, in fact, I mean, it's easy to think of it as this finite graph, and there's just a few states being pulled apart. But this is all in this setting of function approximators that are learning state embeddings, and so the states can actually be high dimensional and continuous. And for example, here and here, the state representation is the pixels, and that means it's technically partially observed, and we don't really handle that, but it turns out that it still works. Yeah. So yeah, you can use high dimensional and continuous representations.
Do you see like how fast is the algorithm since it has to do this kind of like pairwise maximization, or does it not have to do that?
That's all happening during learning. So you're learning this distance function that then at inference time you can apply to any pair of states. And so that's slow, like any learning is. I mean, this is basically a learning algorithm that samples random state, random goal, and just tries to update the parameters via gradient descent to push things apart. So that's kind of a slow learning process. Yeah. Yeah.
So it seems like you've given like a pretty good algorithm for actually optimizing the Quasimetric, but I was wondering about more for like the online RL setting, like the exploration problem still seems non-trivial because right now it seems like you're uniformly randomly sampling like these states and goals.
Yeah.
And that I think works on like the settings that you described, but maybe for like more difficult tasks or long horizon tasks where you need to do like a lot of things to get something interesting. How do you like if you just sample like a uniformly random goal, it seems hard. So I'm wondering if you just have any thoughts about like kind of how you might do exploration in this space in like a more efficient manner.
Let's see. Yeah, that's a great question. We're not really touching exploration right now. There's so many things we're not touching. This is most obviously suited to some offline RL to learn the value function. You can also use all the tricks of online RL to collect trajectories and have some behavioral policy, but we didn't really innovate there. So that's super open question. And yeah, one of the what's next would be exploration, like getting Quasimetrics into the exploration algorithm too, in an intimate way. So yeah, great question. Maybe over here. Yeah.
So like you mentioned how Quasimetric, like you have a method to search over the Quasimetric hypothesis there. But I was wondering if we can turn a similarity metric into Quasimetric by differently encoding states and goals. That also could be.
So not trivially. So you might think that you could do like an asymmetrical dot product. You have f of x, g of y, and that doesn't actually satisfy triangle inequality. So a lot of the constructions that might seem like they should work don't. So you kind of have to come up with the right one. There's a lot of other constructions that could work. The IQE, the interval quasimetric embeddings, works the best that we know of. Yeah.
Like you mentioned that you also have this optimization problem, like a novel optimization problem and this quasimetric thing. Do you have an application showing which of these factors is actually giving the boost?
Yeah, so I tried to show a little bit of that here, and there's actually a lot more of these comparisons in the paper, but this is the optimization algorithm with the quasimetric. This is without the quasimetric, but the same optimization algorithm. And so you can see the quasimetric is essential. And then this is essentially a different optimization algorithm, Q-learning, but with quasimetric, and that actually worked pretty well too. But what I didn't have time to show is that on the continuous control, that fails because Q-learning becomes a lot harder in continuous control. So in the paper, we do a lot of those comparisons, and both are important. Yeah.
I think we can take the questions offline of the talk. So let's thank Phillip for the